Welcome to this explainer. Today, we're putting on our detective hats to uncover the hidden chemical building blocks of our everyday world. We're going to take a really fascinating journey, zooming all the way out from the food we eat right down to the pure, microscopic elements that literally make up the universe. Okay, let's dive into this.
We've got 6 quick stops on our macro to micro journey today. Mixtures in everyday life, the science of pure, elements, compounds, a classic iron and sulfur test, and finally, minerals and wonder materials. Let's get right into it.
Section 1, Mixtures in Everyday Life. And to kick things off, let's look at something incredibly tangible, the food right on our plates.
Take a sprout salad, for example. It is the absolute perfect example of what scientists call a non-uniform mixture. You can actually see all the individual pieces, right? The chickpeas, the tomatoes, the onions, and crucially, they aren't reacting chemically with one another. Every single ingredient keeps its own distinct properties and flavor. I mean, you could easily just pick the tomatoes right out if you wanted to. The parts are physically mixed together, but they remain fundamentally unchanged.
But, mixtures aren't always that obvious. What's really interesting is something we interact with constantly but never actually see, the air we breathe. Air is a uniform mixture. It's seamlessly blended with about 78% nitrogen, 21% oxygen, and little trace amounts of argon, carbon dioxide, and water vapor. It is mixed so perfectly and so evenly that we simply cannot see the individual parts.
So, how do we actually know those invisible components are there? Well, we can prove it with a really simple test. Let's take carbon dioxide. If you fill a glass tumbler with water and slowly add some calcium oxide, it reacts to form a clear liquid known as lime water. Now, if you just leave that clear liquid out exposed to the air for a few hours, something pretty wild happens. The carbon dioxide in the air reacts with it, creating these tiny, insoluble white particles of calcium carbonate. Basically, the solution literally turns milky. And that milky color? It acts as a physical, undeniable clue that confirms carbon dioxide is hanging out in our uniform mixture of air.
All right, moving on to Section 2, the science of pure. Let's zoom in a bit and rethink a word we see at the grocery store all the time.
Now, context is absolutely crucial here. In our everyday lives, when we buy pure milk or pure ghee, we just mean it's unadulterated. No illegal, cheap additives or sketchy fillers mixed in to cut costs. But a scientist? They are way more strict. To a scientist, even that high-quality farm-fresh milk is still just a mixture of water, fats, and proteins. Scientifically speaking, the word pure strictly means a substance consisting of exactly one type of particle throughout. And most importantly, it's a kind of matter that cannot be separated into anything else by any physical process.
Which brings us to Section 3, elements, the building blocks. So what exactly are these pure, inseparable particles?
We call them elements. Elements are the absolute fundamental building blocks of all matter in the universe. They're pure substances made up entirely of identical particles called atoms. And because every single atom in there is identical, an element simply cannot be broken down any further into simpler substances. You can't filter it, you can't boil it, you can't crush it into something else. It just is what it is.
And nature organizes this beautifully. Elements basically fall into 3 main categories based on their properties. You've got your familiar metals, things like gold, silver, iron, and aluminum. Then you have nonmetals, like the carbon and coal, yellow sulfur, and the oxygen we breathe. And finally, we have these fascinating in-between materials called metalloids, like silicon and boron, which act kind of like a bridge, possessing intermediate properties of both metals and nonmetals.
Next up, Section 4, compounds, chemical combinations. Because if you look around, the world isn't just single, isolated elements. We aren't surrounded by floating chunks of pure gold or pure carbon, right? That's where compounds come in. When different elements chemically combine in strict fixed ratios, they create compounds. And this is where chemistry gets basically like magic. These compounds are completely new substances with totally different properties from their original parts. Take hydrogen and oxygen. Hydrogen is a highly combustible fuel, and oxygen fiercely feeds fires. But if they combine chemically in a strict 2-to-1 ratio, they form water, a compound we literally use to put fires out. It's wild.
We can actually see this chemical combination in reverse if we break a compound down. Take everyday sugar. It looks like a simple, pure white crystal, but if you heat dry sugar in a boiling tube over a spirit lamp, you can literally watch it decompose. First, it turns brown, then a charred blackish color. As it gets hotter, you'll see small water droplets condensing near the open end of the tube. And what's left behind at the bottom? A black mass of charcoal, which is pure carbon. The heat has forced the sugar to give up its carbon and water.
And since water is made of hydrogen and oxygen, this simple test proves that sugar is definitely not an element. It's a complex chemical compound of carbon, hydrogen, and oxygen. All right, Section 5, the iron and sulfur test. Let's move to a classic laboratory experiment to really lock this in. This is the ultimate detective test to show the dramatic difference between a simple physical mixture and a chemically bonded compound. We have two samples here. Sample A is a simple, non-uniform physical mixture of dark iron filings and bright yellow sulfur powder, just physically sitting together in a dish. Right next to it is sample B. Now sample B started as that exact same mixture of iron and sulfur, but it was gently heated over a burner, stirred continuously, until a solid, uniform black mass formed.
What's absolutely fascinating is how these two identical starting samples react to basic tests. In sample A, the mixture, a magnet will easily pull the iron filings right out of the yellow sulfur. They completely retain their original properties. But hover that same magnet over sample B, zero effect, nothing. The heat triggered a chemical reaction binding the iron and sulfur into a brand new compound called iron sulfide. And the gas test is even crazier. If you add dilute hydrochloric acid to sample A, it releases hydrogen gas, which is completely odorless and burns with a distinct little pop sound. But drop that acid on sample B, it reacts to form hydrogen sulfide gas, which has this terrible, unmistakable, rotten egg-like odor. The mixture acts exactly like its individual parts. The compound acts like an entirely new creation.
Finally, Section 6, minerals and wonder materials, because understanding these structural rules of matter isn't just textbook theory. It's quite literally the key to real-world innovation. Out in nature, these elements and compounds make up the Earth's minerals. Minerals are basically natural, solid substances with fixed chemical compositions. Most are complex compounds made of more than one element, like quartz or calcite, though sometimes they're pure native elements like gold or copper. These minerals provide the raw materials for basically everything in modern society. The cement in our buildings, that comes from calcite and quartz. It all starts right here with these basic blocks. And today, material scientists are taking this fundamental understanding of mixtures and compounds to invent absolute wonder materials. Take graphene aerogel, for example. It's made from carbon, and it currently holds the title for the lightest material on Earth. It is so incredibly light it can rest gently on a single blade of grass without even bending it. Yet, because of how its atoms are meticulously structured, it's highly porous with a massive absorbing capacity, making it an absolute game-changer for crucial environmental tasks like cleaning up oil spills. That is the true power of understanding matter. So we've traveled all the way from the visible physical mixture of a side salad down to the molecular bonding of iron sulfide and up to the cutting-edge application of graphene. Now it's your turn to be the detective. Take a look around the room you're in right now. Look at the wood of your desk, the glass of your window, the plastic of your device. Can you deduce which objects are mere physical mixtures and which are complex, chemically bonded compounds? The building blocks of the universe are sitting right in front of you, waiting to be understood. Thank you for joining me on this explainer, and keep exploring.